Alright, I'm back with our two enantiomers, R and S2-butanol. I'm going to go ahead and erase the Newman projections from the last video. And in this tutorial I'm going to demonstrate or talk about how chiral molecules interact with plane polarized light. The book has really the best pictures. I'm not going to try to draw plane polarized light, but plane polarized light, so it's polarized in one plane. You'll remember this from high school physics, right? It is an electric vector and a magnetic vector, and they're waves. And so the fact that you have a wave going this way and a magnetic vector going electromagnetic radiation, right? So electric vector this way, magnetic vector this way, actually makes plane polarized light chiral. So like I said, the book illustrates it pretty well. You don't actually have to know how it's chiral, but it is. Plane polarized light is chiral. And what that means is two enantiomers of a given molecule will interact with that plane polarized light differently. So how does that happen? Well, let's say you've got, say that's the plane of polarization. Here's my high-tech gizmo to show that. So we've got light that's polarized in that plane. Pass this light through 2-butanol, and what will happen is the plane of polarization will rotate. And so basically every time a photon of this plane polarized light hits one of these molecules, the molecule rotates the plane of polarization just a little bit. And therefore, if you use standard concentration, so we use a path length of 1 centimeter, we use a concentration, we use that per molar in the unit, and then we use a certain wavelength of light, usually the D line of a sodium lamp. This can be predicted how far this will move. Well, not predicted. It can be calculated based on previous observation. And here's the kicker. So I've shown basically a clockwise rotation, and let's say this is 0 degrees, 0 degrees, and this is 30 degrees. So, and let's further imagine that we've used R2-butanol as the chiral agent. So R2-butanol, under certain conditions, 1 molar concentration, 1 centimeter path length, rotates the light 30 degrees. What do you think the rotation will be if you put S2-butanol in place of R2-butanol? So plus 30 degrees. The rotation is plus 30 degrees when we pass the light through R2-butanol. What will the rotation be when we pass through S2-butanol? Hit pause, think about it, come back. Okay, so let me better. All right, so that's the plus 30 degrees for R. What you'll find for S is it will be minus 30 degrees. So the two enantiomers will rotate plane polarized light exactly the opposite directions by the same amount. So if a standard solution of R2-butanol rotates the light plus 30 degrees, then a standard solution of S2-butanol will rotate the light minus 30 degrees. Okay, makes sense? Go ahead and hit pause if you want, or hang loose while I erase this. Hit pause if you want to write it down. Okay, so what I just told you, the rotation of plane polarized light under standard conditions is called specific rotation, and it's given by this bracket alpha with a superscript D, and in fact there's usually a subscript 25, and what this says is the bracket is standard conditions, alpha is rotation, D is the D line of sodium lamp, 546 nanometers. Turns out that's actually important. And 25 is the temperature, so you do this at 25 degrees C. The wavelength is important. It's beyond the scope of this class, but we get a lot of our information about proteins and DNA, chiral macromolecules, by something called circular dichroism, which takes advantage of the fact that chiral molecules rotate plane polarized light differently than their enantiomer, and that is wavelength dependent. So the amount of rotation depends on the wavelength. So you can take a spectrum of a chiral molecule, see how it changes, and get a lot of information. All right, the question here is, what would happen, what will this specific, or what will the observed rotation be? Crap. All right, hit pause. The brackets are specific rotation. What I mean to ask is, what will the observed rotation specific rotation is the alpha D25. So this alpha is simply the observed rotation. So what rotation will you observe if you have a mixture that's 50% R and 50% S? All right, hit pause, go away and think about it. I will fumble around with my pens. All right, are you back? So if you're back, remember R, which we're designating as the plus enantiomer. So you'll sometimes see pluses and minus in front of chiral molecules. The plus indicates that it rotates plane polarized light clockwise. The S indicates that it rotates plane polarized light counterclockwise. Okay, so the S, under standard conditions, rotates plane polarized light minus 30 degrees. R rotates at plus 30 degrees. So if it's 50-50, what's it going to be? I hope you figured this out fairly quickly. A 50-50 mixture. I wonder if you guys really need all these colors. I like them. Is that on the board? It is on the board. Hallelujah. So if we have a 50-50 mixture, for every molecule of R enantiomer that photon hits, it's going to hit a molecule of S. R flips it clockwise, S flips it back. Hits another S, it goes counterclockwise. Hits an R, it comes back. On average, it's going to hit, 10 to the 20th molecules. On average, the plane won't rotate. No observed rotation, and we call this a racemic mixture, or a racemate. So anytime you have 50-50 R and S, or 50-50 two enantiomers, 50% plus, 50% minus, you have a racemic mixture or a racemate. Okay, one last go. Hit pause if you want. Okay, what will the observed rotation be if the mixture is 80% R and 20% S, or minus? 80% plus, 20% minus. All right, hit pause, give it some thought, come back. Okay, remember, the specific rotation for R is plus 30 degrees. So for every molecule of for every molecule of S that the photon encounters, it's going to encounter a molecule of R and flip back. Basically, 20% S counters 20% of the R. And this gives us something called enantiomeric excess. percent EE. And I guarantee you, if you work in anything that touches the pharmaceutical industry or drugs or biological molecules at all, you'll see percent EE from time to time. It's pretty straightforward to use, and so I'm going to erase the molecules at the top, erase all this stuff, and go through how we calculate this. So the percent EE, the enantiomeric excess, equals the observed rotation divided by the specific rotation. Right? So what we observe divided by what we should observe if it was pure. Right? If it's 100% EE, this will be 1. So the observed rotation would equal the specific rotation. If it was 100% R, we would observe a plus 30 degree rotation. This is also equal to not RNS, plus, this is equal to the percent of the plus enantiomer in the mixture minus the percent of the minus enantiomer. Okay, so down here we need to figure out, so we know the EE, it's 80% minus 20%. So this is equal to 80 minus 20, this is equal to 60. So alpha observed divided by specific rotation is equal to 0.6. So then it's just simple. We know we can replace the specific rotation with what we observe, plus 30. So alpha observed is going to equal 0.6 times 30. So this will give us an alpha observed of plus 18 degrees. Boy, I think that's right. Yeah. This will be the most extensive math you guys do in this class. So the observed rotation will be 18 degrees, and it will be plus whichever enantiomer is in the majority. Right here we have 80% R, which is the plus enantiomer. So the observed rotation will be clockwise, plus. If there was more S, or the minus enantiomer, the observed rotation would be minus. All right, so this is really the equation you want to keep in mind. So it's the EE, the enantiomeric excess, and again, it's the amount in excess one is over the other. It's not 80% R doesn't tell you multiply the specific rotation by 0.8. You have to subtract out the 20. Basically, you have 20% S, 20% R as a racemate. That leaves 60% R as a pure compound to rotate the plane of polarization. Okay, so you need to know this equation, be able to use it. It's just basic arithmetic. Keep in mind that you're just subtracting the amount of the minor enantiomer from the amount of the major enantiomer. What happens if you have a complex mixture? So say it's 80% R, 20% S of 2-butanol, but you also have other chiral molecules in there. What would the observed rotation be? The answer is you can't actually know without knowing the other rotations of the other molecules. The other thing is, this is basic math. It's one equation. So you have to, if you don't know the EE and you don't know the alpha observed, specific rotation doesn't tell you anything. If you know the alpha observed but you don't know the specific rotation and you don't know how much of these guys are around, you can't get anything. So you have to know two of these. So you have to you're either figuring for percent EE, and I gave you percent EE here, or you have to know both of these. If I know both the alpha observed and the specific rotation, I know the percent EE. I'll do another one of these in a shorter homework video. So this is probably good for this video. You've watched a lot. Thanks for your patience. I'll do one more of these as a homework.